Thank you very much for the introduction, and I would first like to thank the organizers for inviting me, and actually it's really a nice opportunity to broaden the horizon with all these different topics. So, well, I'm not the first to speak about superconductors, so I can already refer to some previous talks, but I'm the first to speak about single magnetic adatoms on superconductors. And actually we go really from the single atom scale and want to build up little chains, and actually there the question of topology or not topological superconductivity comes in that I would like to address. Before I start, I would also like to thank the most important people, namely those that were involved in the work. So this is as a PhD student who actually just defended his thesis, Michael Ruby, as a postdoc, Benjamin Heinrich. They are both from my group. And then we have a very, very good collaboration with the group of Felix von Oppen, who's also at our university, and his former PhD students, Yang Peng and Falco Pientka. So, a single atom on a superconductor. So, what does it actually mean from the physics point of view? And actually, I'm going to use the most simple superconductor that you can think of. So, don't think about your that you have just previously heard about these complex superconductors, but just about lead. So, it's a type 1 superconductor. It's a strong electron-phonon coupling, but basically it is about BCS superconductivity. So what you will typically see is this quasi-particle density of states. But then when you put a single magnetic atom, it actually acts on this quasi-particle density of states. And the reason is that if you have a magnetic moment, it can provide a potential for exchange scattering. And depending on the strength of the exchange coupling and of course the spin of your impurity, you will get these in-gap states in the quasi-particle spectrum. So in a very simplified view, you could say, well, if you have a localized spin and you have your Cooper pairs, we are with this singlet superconductor, then imagine that you have some kind of, let's call it an antiferromagnetic exchange. It actually, when you look from the viewpoint of the Cooper pairs, one of them, of the electrons, will be kind of attracted and the other one repelled. And well, this scattering potential kind of looks like you loosen this pairing energy, and this is why the states are located inside the gap. You always find them symmetric around the Fermi level because you do preserve your electron hole symmetry. Okay, so these states, they are called U-Shiba-Rusinov states, or for short, during this talk, I will just call them Shiba states. Well, actually, the question is, most theories, they just simply deal with the spin 1/2 magnetic adsorbate or impurity. And well, in real life, you often have to deal with more complex systems. For example, if you take a manganese atom, you may have even more than one pair of these states. So we always call this one pair, and then you can have additional ones depending on the magnetic moment. And this is something that I would like to address in this talk. But also we ask the question how you actually do transport through these states. So our main technique is scanning tunneling microscopy. We work in ultra high vacuum, so the samples are ultra clean. We can deposit these single atoms. The temperature is 1 Kelvin, unless I stated otherwise. In an STM, we normally speak about the single electron tunneling picture because the tip is very far away and you have your large tunneling gap in between. But you may ask the question, I mean, in this quasi-particle excitation, in order to reach this state, you do actually an excitation with 1 electron. But then it seems, well, once you have done this excitation, the question is, what then? Does the next tunneling electron, can it again induce an excitation or not? And well, if you look at these states, they are really nicely situated inside the gap, so they look very much protected. But in order to pass a current through, there must have to be some processes happening. And as I said before, in real life, atoms may show more than one pair of Shiba states. And then I would like to go to the situation where it's not only a single atom, but you can imagine, okay, more than one atom, they may couple to each other if they are closely separated. And we even want to go to chains that are self-assembled on a lead substrate again. There have been experimental evidence of Majorana states and iron chains at the end of these chains. But the question that I would like to address is this something like a universal feature that happens with 3D transition metals on lead? So do you really get these topological states in all cases? And of course, how this formation of Shiba states goes on. So, as I said, we address this as the single atom scale with manganese atoms, and for the second part, we use cobalt chains instead of iron. Good, so we are not the first to look at single atoms on superconductors, and I should really mention the work that's almost 20 years old by the Eigler group, and at that time Ali Yazdani was a postdoc there, and they looked at single manganese atoms on top of a niobium superconductor. And actually, if you measure at 4 Kelvin, so this is something that you observe in an STM as a superconducting energy gap. Yeah, it's rather broad because you have temperature broadening. This has been measured at 4 Kelvin. And if you then look on a single atom, you do see some variations in this gap shape. And the most apparent thing is actually that you see a change in the symmetry of the height. And this was already correctly interpreted as the Shiba states. But of course, if you increase your energy resolution, you see much better the structure of Shiba states. So this is a work from the Shui group, and they have looked at manganese atoms on lead. And they have lowered their temperature of the STM to 300 millikelvin and additionally looked with superconducting tips. So already if you just compare the energy resolution that you get of the bare superconducting gap that you measure in your tunneling spectroscopy, you see there's really an immense difference. And then due to this improvement of the energy resolution, you don't just simply see an asymmetry and close to the BCS gap edges, but really single states that are located inside the gap. So we have revisited this system indeed. We also look at manganese atoms on the lead 111 surface. So the 111 is the crystal orientation that we pick out for reasons that you will see later. And in the first place, so you see these small protrusions here that are encircled that have been obtained by depositing manganese atoms at ultra low temperature, like at a couple of Kelvin, in the STM, and then they remain individual. So on these manganese atoms, we can park our tip and do the tunneling spectroscopy. So we record the differential conductance, and this is a typical spectrum that we obtain on such a manganese atom. And well, it looks rather busy, so you see many states here, so that's why I would like to walk you through what the origin of these peaks is in more detail. So actually, we also use a lead tip, so we have really dipped it into the surface of lead beforehand and covered it with a sufficiently thick layer that it also becomes superconducting. And then we also have this quasi-particle density of states on the tip. And when we do the spectroscopy, we vary the bias voltage, which means that we align the Fermi levels between tip and sample, or misalign them by this bias voltage. And then, of course, when we have here the occupied states, let's say for the sample, which are really peaked in this BCS peak, just opposed from the tunneling barrier to the empty states, then we see a large contribution to the differential conductance. And this is this region that arises from the BCS density of states of both sides of the tunneling barrier. Now, if we go and ramp the bias voltage, and for example, we reach these states, so these are now just schematically the Shiba states inside the gap. Here we have the electron-like ones that, of course, we can measure them with the hole-like states of the tip. And again, we get very sharp resonances because of this peaked structure at both sides of the tunneling barrier. While in the sketch here, I've only picked one pair of Shiba resonances. We can see here at least 3. So this is this gray dashed region that I named the Shiba region. Now you also find some smaller resonances in this regime, and this is actually the regime where the tip has its superconducting gap. And the reason why we at this energy, for example, see a resonance is that we are still measuring at finite temperature. So this resonance that you can see here is partially occupied, so we have an electron-like contribution that can contribute to the tunneling current and therefore to the conductance in this regime. And this is giving rise to the peaks here that are actually normally in this kind of forbidden region if you were measuring at 0 Kelvin. I don't want to focus on these resonances in the remainder of the talk, but instead I would like to really focus your attention on the other states, and in particular to the asymmetry that you find if you look at the Shiba state that is located at a symmetric energy around the Fermi level. So for example, here in orange, I plot the spectrum, just the one that I've shown before. Actually, the tip is very far away, so this should note that this is our tunneling conductance, 10 to the minus 4 G naught. And if we now focus, for example, on this Shiba pair, then you see here at the negative bias, you see it much more pronounced in intensity than at the positive bias. However, we can tune the tunneling conductance very, very easily by just approaching the tip towards the magnetic adatom. And then you can see, for example, at this increased tunneling conductance that the peaks are almost of same intensity. And if you go even closer, you have really reversed the intensity of these two peaks. So as STM people normally interpret this shouldn't be possible, because then you say, well, you measure your density of states, but that should not depend on the tip sample distance. So there must be something else that comes into play, and this is what we would like to understand in the following. So in order to understand that, we have really plotted the intensity of this peak at positive and negative bias as a function of the tunneling conductance. And this is what you can find here as a plot. So this is the tunneling conductance that we have. And then here's the IDV intensity at positive and negative bias voltage. So, well, if you first approach with the tip, what is totally normal and understandable is that, of course, you have an increase of the peaks as you expected, because you increase your junction conductance. But here comes then this intriguing point. So you have a leveling off of the intensities, and eventually you have this crossing point. So here would be the spectrum where we have equal intensity and at positive and negative bias, and then the intensity has inversed. And the question is, how do we explain this? So at the very beginning, this looks, as I said, a normal tunneling spectrum. So how we interpret it in the single electron picture is, well, a single electron tunnels, let's say in this case from the tip to the sample, and by this it does this excitation that we probe in this quasi-particle density of states. However, in order to measure a tunneling current, you have, of course, a number of electrons per unit of time having to cross this barrier. But if you had done this excitation, then actually you would block the tunneling current if there wasn't some kind of relaxation that allows the next electron to also do this excitation. So if we look into the current that we expect, it is proportional to the tunneling amplitude square, which is just the tunneling process. You have to cross the barrier, but times a relaxation rate that you need in order to empty this state. So now you can imagine that there may be at some point a limiting factor. So by approaching the tip, we're really trying to increase our tunneling rate. And at some point, this relaxation rate is in the same order of magnitude. And at that part of the process, you actually start to block it. And this is the reason why the intensity starts to level off. However, it still keeps increasing. It doesn't stay constant, so it's not a certain blocking. And the reason of this is that, well, we are dealing with a superconductor tunneling junction, and there's another process that can come into play, and this is the Andreev reflection that is happening. So in essence, what you do is you come, for example, with an electron, but this is reflected as a whole, and it goes back into the tip. And you can see there that this process, it never requires any occupation of the states. It all happens within Heisenberg's uncertainty principle. So there is no relaxation rate involved. But on the other hand, because you have to kind of cross the tunneling barrier twice, the current that is associated to this scales with the tunneling amplitude to the power of 4. And the reason then, at this process, when we are really far away, it just doesn't contribute a lot. And when you come close, it of course gains in importance because the other process is kind of suppressed. And this is explaining then our leveling off, but still increase of the slope of the differential conductance with increasing tunneling, with increasing junction conductance. So then we asked ourselves, so this is measured at roughly 1.2 Kelvin, and we have a certain crossover point. And we know that there's a relaxation rate involved. But what is this relaxation that is actually happening? What is driving the relaxation? And I guess the first idea that you could have that is thermally driven, because we are at finite temperature. And in order to test that, we actually said, well, let's measure at 4.8 Kelvin. And if you do the same plot, you actually see, well, in the first part, you have a linear increase. And this regime of the linear increase of the conductance actually remains for a much longer regime, and then you have the crossover at much higher junction conductances because your efficiency of emptying this state is higher at higher temperatures. It's temperature driven. And actually you can do a more thorough analysis of when this crossover happens and deduce even the time scales of this relaxation. So when we are at 1.2 Kelvin, we extracted the life or a relaxation or lifetime then of this excited state of 0.2 nanoseconds, and it's much faster of 6 picoseconds at about 5 Kelvin. So now we understand that if we want to measure in the single tunneling regime, we should sufficiently stay sufficiently far away with the tip. And this is the regime where the rest of the talk is actually based on. So now let's look at the origin of these three peaks that I've been showing you before. But for a while, I want to switch the surface. So now we put these manganese atoms on the lead 001 surface, and the 001 surface has now a rectangular unit cell on the surface plane. And this will help us in the interpretation, as you will see in a while. So similar to the case of the manganese on the hexagonal lattice, we can measure the differential conductance, and we also find multiple Shiba states inside the gap. Actually, you see one very pronounced pair, but there are also some faint resonances, and here I blow up these parts that are dashed by the gray areas. So you can find that this little bump here is really a peak. And you also find a shoulder very close to the BCS peaks that you can identify as Shiba resonances. But I think more convincingly is that these are really resonances and not just some weird shoulders, is that we really plot the differential conductance at this particular energy always. And then you can find certain shapes. So we labeled them alpha, beta, gamma according to the energies. This is the topography that we measure. So, well, an atom just looks like this bump on the surface. But you see very certain symmetries that you can find, and they are distinctly different for the three resonances that we find. And we try to explain this by a very simple model. So if you start with the manganese atoms, you have 5 electrons in the D shell. So actually manganese is supposed to sit in a 5-half spin state on the surface. Well, but what happens to these D levels? I mean, if there was no environment, all these D levels, they should be degenerate. But by the adsorption of the atom on the surface, you actually do break this symmetry and you create a local crystal field. So in a simple sketch, we place here the atom on its most likely adsorption side, which is the hollow side. And then you have here these nearest neighbors. And they act now as the ligand field, and you additionally actually have an atom below. And if you think in this very simplest picture that you could think in electrostatic wise, you actually repel those orbitals the most that are the closest to the nearest lying neighbors. So this is why the dx square minus y square orbital is pushed up in energy the most. Then comes the dz square because it has this atom directly underneath, and these are kind of sitting on the diagonals, and that's why they are lowest in energy. However, this energy level splitting is still sufficiently low that each of these levels remains occupied with the single spin. Actually, when you have almost identical bond lengths between the atoms that are in the plane and the one below, then also these levels remain degenerate. And this is our idea on how to explain now these shapes, because if you look simply at this picture, you would say, well, that actually looks like d orbitals. They are larger, I would like to say. I mean, I really like to stress this is on the order of more than 1 nanometer, so it's not the d orbitals itself. But the scattering potential apparently just imposes the same symmetry from the d orbitals, and that's why you see the same patterns in the Shiba states that you map. And if we look into these symmetries, then we can identify that this is arising from the spin that is still sitting in the dx square minus y square orbital. This one is sitting in the dz square orbital. Actually, this is why it's also so very intense in the center, because also the dz square orbital is protruding the most perpendicular to the surface, so we can reach it the best with the tunneling current. And the fainter ones are sitting really here in the plane, and this is the x, z, and x, y, z, and xy orbitals. So, well, now you see why we chose the 001 surface, because this also has a quadratic symmetry, and that is why it's nicely, I mean, we can write down the energy level splitting like this, but in principle it preserves the symmetry of the d orbitals. So if we go back to the 111 surface, Well, we have seen these busy spectrum. This is the one I was showing you before. And you find the 3 Shiba states. I plot here a deconvolution, which means we take out the density of states of the tip, so that you can really identify 3 pairs of Shiba states. And in this adsorption site, we actually have 5 states. So apparently there are also 2 adsorption sites. We can actually switch between these 2 by STM tip manipulation. But now the question is, can we explain it in the same virtue of what we've seen before? And yes, this works. So let's first look at the state where we see 5 Shiba states. We plot them again. Well, it means if you see 5, you have really lifted all the degeneracies of the d orbitals. But due to the 3-fold symmetry of the substrate, it's not so nicely visible of the d-level shape. It's a little easier for the for the adsorption site that only shows 3 states, because if we again assume a hollow adsorption site, then we have a trigonal pyramidal crystal field, and to very similar arguments that I was telling you before about pushing up the d levels, we expect this kind of energy level arrangement, and then again we can identify the states that we see in the STM. Now, as I said here, it's not so nice to visualize the shapes, but what you can see is that you have a certain long-range extension of the states, and that goes really a couple of nanometers, and here I plot one of these states and visualize it more clearly. So you have something in the middle that comes from the symmetry of the d orbitals, but additionally you can see here this oscillatory pattern that is happening away from the impurity, and actually it has a very distinct symmetry as well as periodicity. Now, where does it come from? Well, the idea is that your Shiba wave functions you can actually write as a part that is decaying exponentially, and that has to do with the coherence length. But there's also a part that is oscillatory, and it actually scales with the Fermi wave vector. So let's see, can we explain this with the symmetries and actually knowledge that we have about the substrate? So lead, in fact, has a very peculiar Fermi surface. And I actually only want to stress and focus here on one part of the Fermi sheet, namely the one where we observe the oscillations from. There's another one which actually does not show up in our measurements. So if you look at this, it is really complex. So you have this tube-like structure, and this is now really viewed in the perspective of the 1-1-1 surface orientation. So you have here this 3-fold symmetry. And well, we see this kind of beams that go along the high symmetry directions, and the idea is your Fermi sheet now here really plays the whole role of the symmetry. Well, electrons that scatter, they also have to, basically obey all these rules that come from the Fermi sheet, and you focus into those directions where you have the most wave vectors basically standing perpendicular. And this is here at these tube-like structures, and this is why you see the oscillations in the particular crystal orientations. Now, additionally, I said that when we look into these directions, we see these oscillations, and here it's plotted along these lines of the positive and negative part of the Shiba wave function. We see the same periodicity is roughly 6 angstrom, but they are also shifted by a little phase. And now the question is, does this fit into this picture of our Fermi sheet? And indeed it does. So if we look into the direction, it's the 1-1-0 crystal orientation where we see these oscillations, then the Fermi wavelength is roughly 12 angstrom. And remembering that we see the wave function squared, we actually see half of the periodicity, and this is why we get the 6 angstrom along these directions, so it actually fits very well. And well, here the shift between the two states at positive and negative energy comes from this phase difference. Okay, so with this, we seem to understand what's happening in the single atoms. We know how to really understand the transport of electrons, what's the origin of the multiple states, and even their extension. Now let's come to the next part where we see chains. And actually, I should there maybe go back a little step, because you're also from different areas, and say why these chains are actually interesting. So one-dimensional atomic chains are discussed in the model of Kitaev chain. And well, if you just plot here your atomic sites, in principle, in the most easy case, it's of course a non-topological state. But if you start to include your Majorana operators and have an effective hopping between the atomic sites, then what can happen is that you remain with here these localized end states at one and the other end of the chain. So, well, what do you need for this? Well, first of course, you need a chain. Second, you should preserve and have a gap. So you need a superconducting state within this chain. And how can you actually do this? Well, it seems easy. You just need to couple a ferromagnetic chain on top of a superconductor. Well, if you take a superconductor without spin-orbit coupling, and it is an S-wave superconductor, and it's a singlet superconductor, actually nothing will happen. But the idea is that lead actually has strong spin-orbit coupling, so it depends really on the spin-orbit coupling in the substrate. And in this kind of sketchy thing, what happens, and actually I think Ami Jacobi introduced it yesterday also in a very nice picture, is that by that you can, if you scatter at the ferromagnetic interface, you can induce triplet superconductivity and thereby induce this p-wave superconductivity that you require here inside the chain. So lead is ideal, it has strong spin-orbit coupling and something magnetic on top, for example, a transition metal. So we are not the first to do this. This is actually a proposal and experiment by the Yazdani group. And they have looked at iron chains and have published this a couple of years ago. So the idea is that you take a lead 110 surface where you have troughs, atomic troughs, and this drives the self-assembly of the iron. And then they also measured with STM, and they find if they take a normal tip, they really find an excitation at zero energy. And they look at the localization of this zero energy excitation, and they find it localized at the chain ends. And this basically led them to the interpretation that this could be a Majorana state. And they also deduced then a topological gap from their measurements. So the question is, if iron is so easy, let's say any 3D transition metal in this simple model should do it. So we thought, let's take cobalt. The growth mechanism is very similar. We also take this surface. It grows along the troughs. So from the topography, they look very similar. But the question is, are they in the first place also ferromagnetic to fulfill the first criterion that you have a ferromagnetic chain? And then the question is about topological states. So in order to measure or detect a ferromagnetic state, what you have to do is you need to take spin polarized tips. And this has been nicely explained yesterday by Kirsten. So just in essence, what we do is we coat the tips with cobalt. And this gives rise to a sort of out-of-plane component. And by that, of course, the tunneling resistance depends on the relative alignment of the magnetic moments. So when they are parallel, you have a large conductance, and when they are antiparallel, you have a low conductance. So we measure this along the chains, and actually we find in the large energy scale here at minus 180 millivolt, we find a spin polarized contrast. So this is due to the D states. And in order to see whether there's some magnetic order along the chain, we take maps at the particular orientation of the tip, and then the opposite orientation, which we have induced by can switch by an external magnetic field. If you subtract these, you see a rather homogeneous signal along the chain. So this is telling you there's ferromagnetic order along the chain. So basically, we have fulfilled the criterion. Now let's look at the small energy scale. So we do find Shiba states inside the gap. Of course, now our tip is not superconducting, so we really have reduced our energy resolution. It's a ferromagnetic tip. But again, we look at these excitations that we find, and we do see a spin contrast in these states. And again, we like to plot this along the chain for the opposite spin polarized tips. And we see some kind of signal also along the chain, which tells us that this ferromagnetic character that we have seen in the D bands is also imprinted now on the Shiba bands that we observe inside the gap. Okay, so that's already one result, that this is kind of inherited. And now the question comes, do we see these Majorana states localized at the ends? And for that now we take a different tip, namely the superconducting tip again, because there we gain energy resolution. We need to make sure we have a peak that's really sitting at zero energy. So now zero energy, of course, because we have the superconducting gap of the tip, now should be at the energy of the tip gap. And we do see signals there. We measure on different chains. And actually, you always see some signal. It actually looks very busy. So before going into the details of all these, I would like to say, let's map again. Do we find a localized state at this zero energy, which is at 1.3 millivolts, because this is the tip gap? And we see, no, the signal is really homogeneously distributed along the chain. So there is no sign of any Majorana mode that are localized at the chain ends. It's independent of the chain lengths for the chains that we actually have investigated. So why are iron and cobalt so different? If you think in a very simple model of these chains, so if you take a freestanding chain of transition metals and you do a tight binding calculation, this is what you find without spin-orbit coupling. You have these strongly dispersing bands, but with spin-orbit coupling, you have the opening of the gaps that are, of course, at a certain energy. And if you compare iron and cobalt, the band structure is very similar, but the band filling is very different. And so here, if we plot the band filling of cobalt, then we actually see that the Fermi energy crosses twice the bands. And well, what happens then, as in topological insulators, if you have two bands, it's not topological anymore. Basically, you have a hybridization between these states. So you need an odd number, and this is not the case for iron. While it could be the case for, it's not the case for cobalt, while it could be the case for iron, which is sitting down here. Okay, so with this, I would like to quickly summarize. I've shown you we can measure electron transport through these Shiba states at a wide range of junction conductances, going from single electron tunneling to Andreev reflections. We understand these multiple Shiba states that we observe as scattering from the different d orbitals. And we also have looked into whether cobalt chains show signatures of topological superconductivity on lead. And with this, as I said, I would like to thank the people involved again, and thank you very much for your attention.